Uh, we are going to start the post-lunch session, and Dr. Tuan is going to present his topic. Dr. Tuan, one request.
Okay.
The request is that whatever you are going to present, we have seen this presentation. You have to make it based on the discussions which you have been attending since yesterday. What is the way forward? And how to create something which is going to be more practical to environmental geotechnology. Over to you, please. Take your 10 minutes.
Okay. Good afternoon, everybody. So today I would present one of my work during my PhD. It is a little bit concerning with environmental geotechnologies. My topic is about discrete element method, investigation of granular backfill pressure in my shaft. Okay, next. Okay, you can skip
this
slide.
you know.
This is something about my informant. And here's a layout.
Yeah, you can start from here.
Yeah. Okay. The problems for the underground mine system, we need to close after exploitation. And one of the structure we need to backfill is the shaft. And the shaft is very special structure with a long, very, very deep and tube-like. And normally, we use a granular material. We utilize the wet rocks, and it's very common to backfill. And the problems concerning with this work is, the first is we need to determine the pressure on the structure in the mines, in the underground system for retaining the backfill materials. It can be plug or it can be the retaining wall. And the second is the stability and also the statement of the granular backfill in the shaft. It is more or less relating to the environmental issues because any instabilities or settlement if occur may lead to the very big issue. For example, the water from surface will go into the mine system. And actually, my topic is relating to one project in Germany. This is for the underground mine system for the salt mine. And when the water enters the salt mine, it can be lead to the dissolution and the big issue relating to the subsidence and so on. Please next. And relating to the pressure on the shaft and along the shaft, normally we use an analytical method, very old theory from Janssen. This is to determine the pressure along of the backfill on the shaft, and actually we can utilize this to determine the pressure on the retaining wall if we have any structure or barrier underground mines. But yeah, the problem is maybe using this theory may lead to the incorrectly prediction, and that's why we utilize the DEM method to simulate the problems. Yeah, the concept of my study here, we use a discrete element method. I don't go deep into the approach here, but that gives a generalized concept of this. We use a very basic model of test to calibrate the parameter, because the parameter to input in the DEM model is a micro parameter, and we need to calibrate using the different model. And here one of the model used for the friction of the particle is a ripple test. And from the different calibration, different model test, we can obtain the micro parameter for the model. Can you click on the right pictures? And when we put in the parameter into to the main model of the mining shaft filling, we can do the simulation. Okay, please, next. And here's some of the information about the material. It's a rock ballast, and using the discrete element method, we try to simulate or to model the grain shape. But actually, with the grain shape, it's impossible. So I try to use a very basic lumps. And also the grain size can be mapped into the PFC model. And after calibration, for example, here the calibration of reciprocal test, we can obtain the parameter, the relation between micro parameter and the angle of reciprocal, and we can determine some change, and we can obtain the micro friction. After that, we put in the main model of shaft backfilling. And on the left side, you can see the sketch of the model of the backfilling work in the rain test. Actually, we have I have the data from the main test here, and I just try to simulate the main test into the 3D model. Okay, next. And here are some parameter. I think it's not, we don't need to go too deep into the details. And from the simulation, we can obtain the results. For example, here, the relation between the pressure and the depth, both vertical and horizontal. And we can also obtain the pressure ratio, and also the one small parameter is porosity. And it's interesting here, the porosity from the model we obtain is similar to what we obtain in the rain test. And yeah, by compare between the simulation result and the analytical methods, we can see the difference. And as we observe here, from the Jensen method, the depth of wick, the pressure become saturated is higher than prediction by the 3D discrete element method approach. And we have the comparison with the result from the rain test. Actually, the simulation from 3D discrete element method is more closer to the rain practice. Yeah. And here the obtain from the simulation, we can obtain the new formula. Yeah, I call it the modified Jensen method to determine or to predict the pressure along the shaft. And yeah, and by using the model, we can also simulate how the behavior of the backfill column in the mine shaft and how it occur. We can determine the maximum or critical load of the plug on the plug to the granular column. And here is that one example. And here's some conclusion. Yeah, we can follow the backfilling problem using the 3D model, and it can be successful simulated. And yeah, I address here some of the limitation also, for example, the symmetry model or some of the minor factor relating to the model, I think is not so important. And the most important for my result is the obtain or the derived formula for the pressure prediction. And some of the problem relating to this, maybe I can address. For example, in case of we cannot, so far I haven't deal with the problem when water or there's a water, groundwater inside the shaft or something like that. And maybe in different kind of different shape of shaft maybe lead to the different results. That's all from my presentation.
Thank you very much.
Thank you.
So I'm sorry I could not attend your presentation, but any delegates, if you have a question or discussion, yes, please.
Yes, sir. Can I ask?
Okay.
So you have simulated with all spherical particles.
Yes.
Okay, so but what is the approximation, dimension, how you have approximated with that? Because there are all irregular particles, but you have assumed in DEM as spherical particles.
I use I need to upscale the size of the particle in the model because the number of element in the numerical model is influent to the computation efficiencies. And as I final scale is I remember 5 up to 5 times, and the time of simulation for me take nearly 3 months. Oh, that's the feeling. That's the final.
And the grain size distribution, what you have said, so that is the type of spherical particles you have considered, or all are of same size?
Different size.
Different
I have a thread
grain
in.
size distribution.
Yeah, I map exactly the grading curve to the model with a different size.
Different size sphere.
Yes, yeah. And with my code, I can manipulate the grain size distribution. And this is one of the advantages of my models.
So you don't use any technique to create different shapes, non-spherical shapes.
No. At first, I try to do that way, but finally, I found that it's got a lot of time and it's not effectively or inapplicable because we can build up the ring shape, but different for the ballast assembly we have a different shape. Yeah, my colleague, one guy have mapped the shape, but he builds he used another approach that builds the formula on the distribution of the grain shape and the grain size. There is a relation, and he tried to, but not exactly the ring shape. Because using the ring shape, we can build up the shape using many particles combined together, but it's cost the computation a lot.
But you just change the diameter, but the equivalent diameter.
Yes, equivalent.
Angle of repose also you have considered, that angle of repose.
And yeah,
So that correspond to spherical particles or your original angular or some size?
yes. I have the test for the angle of residual, and then I simulate similar to what you see here, and by input the micro parameter, we can see the relation, and we compare the angle, the ring angle of residual to the result of the simulation, and we can obtain the micro parameters. Block effect?
Plug.
Plug?
Yeah, that's retaining wall or plug.
Yeah. That from my simulation, I just obtain the pressure on the plug. And of course, if we can see the, if we need to see the behavior of the plug, we can, use the particle to build up the plug elements. Yeah, and then we can see the behavior. I think it is another problem.
Because in your simulation, the particles are dry.
Yes, totally dry. Yeah, no water at all. Yeah. So when we, I think if we need to simulate the behavior of the granular under water condition, maybe we need to use a coupling method, or maybe we try to assume. We must use some assumption.
But here I think if you can consider the angularity, sphericity or morphology of the grains itself, then that will give you more practical results. So whether like that can be put as an input parameter here, angularity, sphericity, basically roughness,
You mean
basically
character of
grains,
the particle?
morphology of the grain
Yeah,
itself.
yeah. Yeah, that's similar to his questions. Yeah. At first, I try to describe the morphology of the particle, but later on it's inapplicable to the simulation because the number of particles will be a lot. So my final model is about nearly 100,000 elements, 100,000 particles, and it takes for me nearly 3 months. Yeah, for that to drop out the particle, and actually the main result is from the scale up of the five times of the ring size of particles, and I use that 2 or 3 particle clumps that combine 3 bow together to create a new particle.
Okay, thank you very much.
Thank you.